Greetings, everybody. We're going to go ahead and start the webinar here and get going. Hopefully you are here to see the ASBI February webinar. Mr. Ben Soule is Technical Director at Sistra IBT, and I'll introduce him here in just a little bit. And he will then lead our presentation this morning or this afternoon, depending on where you are. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. I'd encourage you to follow me on LinkedIn if you're not already, and also follow the American Segmental Bridge Institute. You'll see announcements about activities like this webinar, as well as other things we host throughout the year, as well as just some interesting information about segmental bridges throughout the year. Some quick announcements. Next month, the March webinar will be March 30th from noon to 1 Central Time. Tom Stelmack with Parsons is going to share with us about the HART Airport Guideway and Stations project that they did in Honolulu. And then our April webinar is also already lined up. Wally Jordan and Russell Dingman from Kiewit are going to talk about a very unique extra dose finback design that they did for the Selman West extension in Florida. Another upcoming event that ASBI is hosting is our grouting certification training is April 11th. In Austin, Texas, it's going to be in-person training this year. It will be the only in-person training event we do. In fact, we're not planning to do any webinar training events after this one. So if you are in a position where you need grouting certification training for your job, or even just for general knowledge, and encourage you to go ahead and sign up for that training here in Austin in April. Another activity we have also in Austin this year is our annual convention is October 31st through November 2nd at the Hyatt Regency in Austin. Registration is not open just yet, but we expect here in the coming weeks to have a registration site available on the website. But for now, you can certainly add that to your calendar of events and plan to join us here in Austin for convention. So some quick instructions on how the webinar will work today. If you lose a connection at any time during the webinar, you can just rejoin with the link you were provided. You will miss content while you're away. It's kind of like when you step out of a room in a live setting. Certificates will be issued to those who meet the minimum time requirements in the session today. I'd encourage you to stay through the entire Q&A if you can, but certainly if you need to move on after the presentation is over, and certainly understand that. We're going to try to wrap up at the top of the hour, but we may run a little bit long depending on how far we go on Q&A. So you don't have to stay for the entire Q&A in order to get the certificate. Also, a little reminder, allow us to give about a week to get certificates out to you. We don't use a system that generates automatically by email. We actually verify attendance and time in attendance before we issue certificates. The system we use requires us to do that through our CEP. So we'll also do question and answer at the end of the presentation. As I mentioned, the way that'll work is you should find on your control panel a little questions tab that if you click the questions tab, you'll then be able to type into a question box any question you might have. I'd encourage you to do that as it sort of comes to you. We're going to be collecting those questions throughout the presentation, and then Ben and our moderator for today, Tim Berry, will go through a little Q&A session to address as many of the comments as we can. If you're on a mobile device, then you should have a little question mark in the upper right-hand corner. Just click on the little question mark, and again, you'll have a little pop-up pane to be able to input your questions. Again, we are doing professional development hours through RCEP. You'll be issued a certificate for attendance today, and this is just sort of the splash screen we're required to provide that shows that we have met the continuing education program requirements for today's presentation. So with that, I'm going to introduce our speaker, and then after I introduce Ben, I'll switch over and share screen and let him share his presentation with us today. But our speaker today is Mr. Ben Soule, the Technical Director at Sistra International Bridge Technologies. Ben has spent over 25 years designing segmental bridges, starting with J. Mueller International and then at International Bridge Technologies since 2002. So I guess this is an anniversary year for you, Ben. He has experience with all types of segmental construction, including a number of design build projects. He's been an active member with ASBI for decades and is particularly interested in construction practices and segmental applications for rail bridges. So with that, I'm going to turn over to Ben as our presenter.
All right. Well, thank you, Greg. I appreciate that. Give me a second to get
All right. Thank you, Ben. And yeah, we can hear you just fine. So.
Okay. Is slideshow looking good?
Yep, looks great.
All right. Well, thank you very much. I'm thrilled to be here today to talk to everybody, and I can assure you that that picture you saw was about the midpoint of my anniversary, but I'm at least confident that my picture is not any older than the one that Tom Stelmack had there. So today, this is meant to be a real basic grounding in segmental. What it is, how it works, what the terminology means, how things are cast, how they come together. So if you've had questions that you've always wondered about, never really understood what a term meant, or how things really come together, this is the place. Don't be shy to ask. This is what it's for. If you are an old hand and have been to 15 different ASBI conventions and built a handful of projects, you may not learn a whole lot, but you get the PDH either way, I suppose. So quick overview of what we're going to talk about today, just what segmental construction is, run through some of the major types of segmental bridges and just talk about how they come together. Look at a casting yard, how a casting yard works, geometry control, post-tensioning, and last direction equipment. So tend to run a bit long, so I'll try to auctioneer my way through this presentation. So what is segmental bridge construction? Well, segmental bridge construction is a technique where the bridge is divided up into pieces. Whoa, that is not what I meant to do. Well, I'll leave the picture on there. It's a little better to look at. So a lot of people in bridge construction are familiar with the idea of working with girders, and that's kind of taking longitudinal slices of the bridge for each girder line. Segmental construction is really 90 degrees to that. The bridge that you want to build is cut up into slices. So you take transverse cuts along the bridge that you want as a finished product, and those pieces are fabricated individually. They can be fabricated individually on site, cast in place, or they can be fabricated off-site, and that's precast. So these pieces on average are roughly 10-foot slices. You know, if you've got special conditions, you can do a little bit longer than that, or a lot longer than that. But order of magnitude, you're dividing the bridge up into 10 to 15-foot slices, making each piece individually, and then assembling them on site to create the completed structure. And that's where the post-tensioning really comes into play. A little bit of terminology on some of the parts and pieces just to get oriented to what we're talking about here. So a typical segment, that's kind of what you see over here. So typical meaning it's sort of along the length of the span, it's sort of the basic shape. And I should mention that a lot of segmental construction, probably close to 90%, uses this basic trapezoidal box girder shape. It's proven to be something very efficient and economical for segmental construction. So a typical segment is just a segment, one of those 10-foot slices that you would find along the length. A pier segment, those tend to be a little bit different. When you get to a pier, you are transferring a lot of load from the span into the substructure. So you're going into bearings a lot of the time. Sometimes you might have a monolithic connection. And there's a lot going on there force-wise. So you need a diaphragm, that's the next word, this concrete infill, to really achieve that transfer from your typical section into your substructure. A variable depth segment, so a lot of times if your spans get longer, you want them to be deeper to give you more capacity at the pier, and you can sort of see that as it heads over this way. Let's see here. So variable depth, usually keep the top part the same, and the bottom gets taller as you go towards the pier. So you'd be skinny in the middle of the span and taller over here at the pier. And the last thing is a precast substructure. We'll touch on just briefly, but you can also do columns. So precast segmental is not just for superstructure. you can have precast segmental columns as well. So moving on, looking a little bit more in detail at one of the segments. So this is some of the parts and pieces of a typical segment. So a segment joint, that's just the face of the segment. That's where you take that transverse slice in the bridge. Top flange or top slab, this piece along here. So it's the top part, usually the driving surface or the riding surface for rails. Bottom flange, bottom slab, same thing. The web is the vertical piece that connects them. Shear keys, when you see these bumps and indentations, you see some in the top, some in the bottom, mostly along the web, those are the shear keys. Tendon anchors, so if you see a big square piece of steel with a hole in it embedded in the segment, that's what that is. That's the anchorage hardware for a tendon for the post-tensioning. And then when you see these sort of bumps and blockouts here, these are blisters, and that's commonly used to anchor a tendon sort of in the middle of the span. So you need a way to pull that anchor out of the section if you don't have access to it, and get the jack on it. And the last thing to mention, PT bar blisters, we'll talk about what those are for, but again, it's for part of the post-tensioning when you start to erect the bridge. So first going to run through the different types of segmental bridges, and we're going to start with cast in place segmental. So cast in place segmental, that means that you are casting these pieces more or less right where the bridge is going to exist. So you're casting them along the alignment, and you're working your way out in pieces, in segments. So mostly this is used as progressive placement of some kind on previously built structure. So you're building your way out, and you have a lot of needs for specialized forms. So by far the most common bridge that you'll find in this category is a balanced cantilever. A lot of times you'll see 3-span balanced cantilevers done cast in place. That's a very typical usage. And these are usually in response to kind of one-off difficult crossings. Maybe you need to get over a river, rail yard, highway, something else. You need a longer span, and you have pretty poor access on the ground. So you'll see that for the main span, and then the construction technique really lends itself to a 3-span configuration. But the way it works is right there in the name. It's a balanced cantilever. So you are building out from a pier and cantilever. So that's what's happening here. You start at the central pier, work your way out. That's the cantilever part. The balanced part is you're doing it on both sides, right? You don't want to have a big imbalance from one side to the other as you build. So you're trying to stage your way out, working your way out from the center, and balance cantilever. When the cantilevers coming from 2 adjacent piers meet, you secure them together and you cast a closure, and you have a continuous span. So for a lot of these, I'll sort of give a schematic of the PT. While you're building the cantilever, you are stressing cantilever tendons. These are tendons that you see here in blue. These are in the top flange, so they are counteracting the negative moment from the dead load cantilever. So every time you cast a segment, you're stressing a tendon to sort of counteract the action of that segment. This is a cutaway view. Obviously, bridge doesn't look like this, but looking at the bottom slab. So once you join the 2 tips together, you have a continuous span. Now it can take positive moments, tension on the bottom. So you have to have continuity tendons. That's what those are typically called in blue there, that run along the bottom flange. So these you can sort of see there. You don't have a free edge. This is where the blisters come into play. So you would have blisters to anchor and stress all of these tendons once you have continuity. Another type of cast in place bridge are cable stayed. These are obviously less common and really just an extension of the same logic, right? You have something that's difficult to cross. In this case, they're usually a whole lot bigger than what you would do for a cast in place balanced cantilever. So getting up into the 1,000+ foot range, these are major crossings. The concept is very similar. You're really doing the same thing. You're building your way out in cantilever from a center pier. In this case, you're substituting the cantilever tendons for the stays, but they're really playing the same role. They're giving you that capacity to handle the bending as you work your way out. The one major difference between the two, other than the cables obviously, is you need to find a home for these cables. You need to find a way to anchor them. You have a real big concentrated force in a real small area, so you need to find a way to put that force into your structure safely. And a couple of ways that you do that. You see a lot of anchorages along the edge. That's what you see over there on the left. So that's an edge girder type application. You would have that on both sides of the deck, running your way out. Just looks a lot like a typical blister, only difference being they're usually a whole lot bigger. The other one is on the right. This is an old picture. This goes way back in segmental, but it's the idea of a delta frame, maybe a phrase that you've heard. There are different ways to put this together. They can be concrete, they can be steel, but what it is a way to take the concentrated load you see here coming from the stay and distribute that load into the webs of the structure, right? You have a vertical load, you want to get that into the webs. So that delta frame is what does that job of distributing the load. And then you have a big blister here to sort of house the reaction from the stay cable. Getting even more rarefied, you can use cast in place segmental for arches. Pretty similar. In this case, it's not a balanced cantilever situation. It's a unidirectional cantilever, right? So you need a way to keep that under control until you have continuity. In this case, this Hoover Dam Bridge, they're using these temporary stay cables to stage it. Once they meet in the middle, there'll be a closure pour, and those cables will be taken down. You don't see it very often, but they really are impressive when you do. And then the last one that falls into the cast in place category is incremental launching. That's a little bit of a twist. So in incremental launching, instead of casting each piece where it's going to exist in the final configuration, you set up a miniature casting yard behind one abutment, and that's over here in phase one. And you cast on pieces, you add pieces onto the bridge, and then push them forward across the alignment. So that's what is happening here. You can see segment number one gets cast, and as you cast more and more segments, that segment one is getting pushed across the valley. So relatively rare, but it's good for certain circumstances where you have poor access on the ground, but you really don't want to make an investment in major equipment. There's not a lot that you need here to make this work. So it's one that you see that falls into the cast in place segmental family. Touching on the PT for those incremental launches, you can sort of see and intuit as you're pushing this thing across. You're going back and forth between positive and negative moment, right? You're supporting it everywhere at one time or another. So you need tendons really every which way, and they sort of end up looking like this. You have tendons going up and down, and really you're just compressing the heck out of that section to make it work as you push it along. Now, something to point out about all of these different cast in place methods is that because you're casting directly against the other segment, you have the opportunity to have continuous rebar, and that's what you see here in this picture is the segment that was cast, earlier. They're going to cast another segment against this, and you can see there's a lot of rebar sticking out, right? Because your first pour is your final pour, they never come apart, and that gives you some advantages. And you can see there are not a lot of shear keys on the face of this segment. You don't really need to do that as much because you have this continuity from the rebar sticking out. Now, switching gears a little bit, I'm going to talk about precast. So in precast, it's an entirely different situation. The segments are precast offsite. They can be quite far away, 100 miles away. They are transported to the site and assembled. You usually need some specialized equipment, both in terms of casting the segments, you need the forms and the molds, and to assemble the segments. So this tends to be used in more high volume situations. Maybe you have poor access, a job over water, somewhere where you can't put down false work, congested city, something like that. But you do need a fair amount of volume to make the investment in the specialized equipment work. So going to walk through the basic types for precast segmental, starting with the easiest one, and you can tell it's the easiest one because it's called the simple spans, but it's span by span erection with simple spans. Very first thing you learned in an engineering class, just a beam supported on either end, free to rotate, easy. You can almost design it by hand. So it's just a simple span supported on a pier on either end. It's probably the fastest way to build. There are no closure pores to deal with. You can just keep going. You have the shortest erection cycle. The downside is it's a simple span. It's going to have the most limited span range. So the sweet spot for these is on the order of 100, 125 feet, 120 to 125 feet, sorry. You can see a little bit nibbling around the edges on either end, but that's roughly where you're going to live with that type of construction. Next, oh, sorry, forgot PT. So the PT is, again, very simple. So the PT is self-contained within the span. It anchors in the diaphragm on either end, and it follows a drape pattern to give you resistance to the positive bending that you see for a simple span. So very straightforward, kind of easy to understand how that works. The next step up in complexity is span by span made continuous. So in this case, you are still building one span at a time, working your way along the alignment. The difference is with each span, you are creating continuity with the previous spans. So this is done with a combination of closure pores between them and post-tensioning that overlaps. So it does have a slightly longer erection cycle. You have to take some time to put in these closure pores at, a day or two on an erection cycle. The reward on that is it allows you to push your span lengths out a little bit longer. So here's a schematic of sort of how that looks. So this is a 4-span unit. You can see there are closure pores at the piers. So this is to keep the geometry going well and to create that continuity from one span to the next. So there are a number of those to pour as you work your way out. And then it's subtle. A lot of people would look at this and say, well, that's the same PT you just showed me before. The difference is over here. If you look at this pier segment where you have continuity, you'll see these tendons overlap with these tendons. So that gives you that continuity. It gives you the compression for negative bending over the pier, and it creates more of a continuous unit. Usually you see these from 3 to 5 or 6 span continuous units. Now we talked about balanced cantilever for cast in place. You can also do balanced cantilever with precast. So very, very similar in concept. The difference being that instead of casting these segments in the cantilever as you go, you are casting them elsewhere and you are assembling them in cantilever. But the idea is the same. You're adding a segment to either side, working your way out in a balanced cantilever, stressing cantilever tendons as you go to combat that negative moment. The big thing with these is transportation weight. And that's really the limiter on what you can do with these in terms of span lengths. So this is one that was done on land, and roughly speaking, they can be divided into delivery by land, taking things over highway, and delivery by water. When you're delivering by land, typically kind of limited to about 15 or 16 foot depth, and that's going to reflect itself in limitations on your span length somewhere up to around 300 feet. So you would build this out to 300 feet, and then you see over here, hopefully it's clear enough, when the tips meet together, you do have cast in place closure joint between the two cantilever tips. Sometimes you might have construction joints at the pier table too. Those can kind of go either way. There are lots of ways to address that particular problem, but the delivery is often the limiting factor, the weight, the height, what can you get on site. It's not as clear as I hoped, but this is an example of the Oakland Bay Bridge where delivery was by barge. So there was a lot more flexibility in a project like this to go big. So the span lengths were a lot longer. This was getting out over close to 500 feet, I think. The segments were a lot bigger. They weren't limited to that 10-foot length. Everything was done in water, and you could take bigger bites on a bigger bridge. So those are kind of the things to think through when you're laying out a project like this is, how am I going to get things there? How am I going to erect them? What sort of access and delivery do I have? So just like with cast in place, you can take precast and you can do cable stayed bridges with it here. Again, very similar concept, same construction. You're working your way out in cantilever and using the stays, to handle those negative moments instead of the tendons. Again, segment transportation and planning the moving and erecting the segments is an absolute must. How are you going to get them there? How are you going to lift them? How are you going to deliver them? Are the stays going to be in the way? If you're trying to deliver them over the deck, do I have access to pick them from the water? Those are certainly things that you need to think through as you work on a concept like this. So, and then the last thing for the precast options, precast substructures. So I guess if we really wanted to, we could claim that regular cast in place columns that are done in lifts are cast in place segmental. Nobody's really tried to take ownership of that yet, but you can also do precast substructures. It's a nice, very efficient, very quick way to put things together. The segments are cast just like the superstructure. They're post-tensioned together, combination of bars and tendons usually, and post-tensioned into a cast-in-place foundation. So when and where do these make sense? Well, they make sense from the point of view of speed. They're very nice. They come together very quickly, but a little bit of fuzziness when it comes to how well they do in seismic zones. I don't think the ductility requirements are well understood or appreciated in a lot of places that have high seismic, your Californias, Washington, what have you, typically don't want to see these. But somewhere like Texas, it's a much easier sale when they make sense. A couple of things about that are sort of common to all types of precast segmental. We talked about shear and alignment keys. So this is what the face of a precast segment looks like as it comes together. And you notice there is no continuous rebar here, right? You cast them together, separate them, bring them back together on site. All those bars would get smushed. So there are no continuous bars. That does have implications for design. It means you have to have be a little bit more conservative in other places in the design of the bridge. Construction-wise, it means you have a lot more of these shear keys. So you can see that really the hardest working ones, the highest density of these keys are along the webs to help transfer that shear. We also have a number along the top and bottom. Sometimes people call these alignment keys, and they do play that role. As you bring the segments together, they sort of force any little imperfections or deflections in the segments together, force them to match up well so you don't have little bumps where the segments are meeting. Those are alignment keys. All precast is connected with epoxy. Some of the old timers like me and above will tell you that there used to be a day when you didn't use epoxy on certain types of bridges, but at least in the US, those days are gone. According to ASBI, all precast segments need to be epoxied together when they are assembled in the site. So this is an epoxy that you can see I'm applying to the face here. Read your specs carefully, make sure you understand your needs for epoxy, whether it's one side or both sides, and what you're supposed to do with ducts and things like that, and understand the limitations of how long you have to work with the epoxy. It'll start to harden within an hour, depending on the product and the temperature. It can take a little bit longer. Now, just joining them together with epoxies is not quite enough. That epoxy needs to be squeezed. And almost every type of segmental construction, you'll have some sort of temporary compression to squeeze the epoxy together to make sure that it's really getting in, that you have a good flush connection between two adjacent segments. So hopefully you can see what's going on here. There's a segment joint over here. These post-tensioning bars are squeezing that segment joint together. The epoxy comes squeezing out. Make sure that you have a good finish and that it's really sealed all the way around the perimeter. So next topic, casting yard. This is for precast only. Obviously, you don't have a casting yard for cast in place. You'll hear two different phrases when it comes to casting yards, long line and short line. Long line is not that common, but I'll just mention it here. Short line, majority of the segments that are built these days are short line. Example of long line casting on the left, short line on the right. And in a little more detail, with long line casting, you set out the geometry of an entire span or an entire cantilever with your forms. And that's what's happening here, again, Oakland Bay Bridge. So you can see the soffit form lays out the geometry for the entire thing. You would adjust it with these jacks, sort of get the profile that you want to cast. And then they have some movable forms as they work their way along the side to cast it. So you sort of lay out a cantilever or a span all at once and then cast it in pieces and then separate them. Short line, you are casting one segment at a time. The form can only accommodate the length of one segment, so you're constantly rotating out and putting new segments in to match cast against them. So much smaller investment in form. You can fit a lot more forms in one place, but again, it's the most common type of construction that you see. A few parts and pieces of the short line casting setup. So how do the forms work? What are the major pieces? So this is the setup for casting a segment. And it shows you a couple of things that are important here. One is that segments are match cast. What does that mean? It means that each segment is cast against another segment. That's how you get the geometry. That's how you get them to mate up properly when you assemble them in the field. So this segment here, a previously cast segment, is a match cast segment. This empty spot in the form here is where we're going to cast a wet cast or a new cast segment. So you see the external form, that's the outside shape of the segment. Here in red along here is the fixed bulkhead, so that'll create that face of the segment. You have a core form. The core form needs to be able to slide in and out to form the interior void of a segment. So this segment will be cast against that one, and it'll be formed by those four sides. This is what that looks like in practice. So what are we looking at here? This is a top view of a segment about to be cast in a short line form. So taking a look at the parts and pieces again over here on the left, this is the match cast segment. So that'll be one side of the form. Right here, you can see the shear keys sort of as part of the fixed bulkhead. So that's the fixed bulkhead on that side. It never moves, hence the name fixed. And then you can see all the rebar and underneath it, the top of the core form for the segment that is about to be cast. So I have a short video of how that comes together. Hopefully this will come through nicely. But so here's the segment that's going to be used as the match cast. So it's adjusted to get the right geometry. It's on hydraulics to let it move around. You bring the rebar cage in. The core form slides in from the end. It gets filled in with concrete, hardened, and then the match cast segment is taken into storage, and the segment you cast the day before is moved into the match cast position to cast the next one. So this is ideally on a daily cycle. You certainly want to turn these forms as quickly as you can, and every casting yard aims to try to get a segment per day per mold. And to do that, it helps to do a lot of prefabrication, especially the rebar and the post-tensioning that is going to get cast into the segment. So usually behind the molds or in close vicinity to them, you will have a rebar jig, sort of a template, so that the rebar for tomorrow's cast can be tied today. All the PT hardware is tied in, and you get the whole shape so that it can be lifted, just like in that video that we just watched, all in one piece when it's time to cast the segment. I sort of just casually mentioned that the segments are taken away and put into storage. You need equipment that's going to take them away and put them into storage, some sort of lifter, MyJack type situation like this. So that needs to be accounted for in a casting yard and in the design of the segment when you pick it up and move it around. And storage. You see a lot of pictures like this of segments cast in storage. Depending on the size and layout of the yard, you are going to need to store segments for a while. At a bare minimum, segments are usually 28 days old when they're erected. So casting yard needs a lot of storage space. Some folks like to try to make best use of that storage by doing the double stacking, and you can see the engineer in me is coming out here and bold text. You don't do this without approval. You don't just do this on a whim. They are putting pretty significant forces on the segment. You need to make sure your ducks are in a row there, and that nothing is going to get cracked or damaged. So they're stored on dunnage, and I want you to pay close attention to how these things are sitting on the ground. So in this picture, you look under the web and you can see two of these sandbag supports underneath it. And as we go to the next picture over here, you see a single sandbag support on one side. So this is really the way that they're always stored, is this 3-point support. Why do you do that? You don't want them rocking. If you put in 4 points, it's like a 4-pointed stool, and you always have one corner that's a little bit lower than the others. And in this case, it's not the rocking that's an issue, but it's the fact that since concrete creeps over time, it'll start to try to twist to set itself down on that 4th support. And then when you fit them together in the field, they won't fit together as well. So you always want a 3-point support, one under one web, 2 under the other, to prevent that twist from creep. We'll talk about delivery. So this is what you usually see for a land-based project, delivered on kind of a lowboy trailer. It is something you want to vet very well, the route between the casting yard and the construction site, to make sure that you can get under or around all the bridges. Water transportation, of course, has a lot more flexibility, and limiting is usually around a 15 or so foot segment. And as you plan this out, don't forget about these. If you have barriers, parapets, anything like that sticking out, that adds onto the height. So you can see these were bent over in this case, and sometimes for taller segments, people will use couplers to limit that height. So make sure you're all in on your clearance envelopes. Now, next topic, geometry control. And geometry control is really a key part of how this works and how everything comes together. So understanding geometry control is really one of the more challenging parts of getting your head around all this comes together. So, if you're working on a fairly conventional bridge, cast in place, whatnot, casting a deck on a typical girder bridge, you're on site. You have an alignment, you can survey where it's supposed to be in space, and that's where you are setting your forms, right? There's a relationship between where you are working and the geometry and the profile that's on paper. With segmental, that's not always true. Cast in place construction, obviously you're a lot closer, but cast in place construction has its own challenges in that it's a moving target. Precast construction, you are casting things miles away. So you're nowhere close to the site, you're not surveying it into position in any way. you are trying to recreate a geometry somewhere else that you will then transport to the site and assemble and follow the correct geometry. So it takes a little bit more thought. And I'm going to work through the two different types of construction, cast in place and precast, to see sort of the big picture of what we're trying to achieve and how it's achieved. So in cast in place, this is a bit of an extreme example, but this is a cast in place balance cantilever on a very tall column. And just intuitively, you can look at this and appreciate that when I pour tons of concrete on one side, it's going to lean over, right? So, and then I go back and pour concrete on the other side, it's going to lean back the other way. That's what I mean about a moving target, is that a lot of cast in place construction, things are moving around as you are casting the concrete. And the question that really gets to the heart of that is, where do I want to set my forms today for this pour, so that when I'm done rocking back and forth and stressing tendons and doing all the things that I'm going to do, I end up at my target elevation. So that's the goal. You need to set your forms somewhere that is not on the profile, so that when you are done making all of these steps, creep and shrinkage is a part of that too. As you go through the construction cycle, I want to end up somewhere. Where should I start? And this is a picture. Give me a minute, I'll explain what's going on here. It's a little bit bare bones. It took me an embarrassing long time in my career to understand exactly what's going on here. So this is a picture of a model. So you would be working your way out from up here over here, sort of doing your balance cantilever construction. And it's stage by stage model. So you're modeling the construction of each segment as you work your way out. So in this, the dashed line up here is your target profile. This is a deformed shape that you might get out of a model that you're doing analytically. And the technique that you always see is to initialize at 0. That's what this red one. So if we're building in this construction step, we're building this segment, you always initialize the tip of that segment at 0. You put it on the alignment, 0 deflection. That's not what you actually do in the field. It's just an analytical tool. The reason it's an analytical tool is that if you initialize at 0, then that node, that point in space, starts life at 0 deflection. And it may go up a foot, down a foot, up 2 inches, down 3 inches, all kinds of things for all the steps that come after that. But the number that you have at the end, after all your construction steps, after all of creep, is the total deflection that it's had over time. It starts at 0. Whatever deflection you get at the end of all that stuff, that's how much it's going to move from the time it is built to the time that you're done constructing. So that is the number that you use to set the forms, right? If you find out that all of that stuff happens and at the end of that it is up above the profile by 3 inches, then you would want the form to be down 3 inches when you cast it, right? So that it ends up at 0. One big caveat, and I underlined it here, is most engineers don't account for traveler deflections. They don't have that stiffness in their model. So you need to take into account how much the traveler is going to move down itself when you put all that wet concrete in there. And it can be, an inch or so. It's not insignificant. So that's sort of the theory of how cast in place geometry control is done. Precast is a whole different kettle of fish. So precast, you are trying to recreate the geometry of a span that can be doing all kinds of things out in the field, right? So you might have a bridge that is curved in plan. It could be going through a vertical curve and profile. It could be twisting, right? A change in crossfall as you go from one end to the other. So you've got all of these geometric variations that you want in your finished bridge. But all you are doing is casting one segment at a time. You are taking 10-foot chunks and casting those in one of those forms that I showed you earlier. So the whole idea behind it is that you want to look at each 10-foot chunk and recreate the relative relationship between two pieces in the form. So if you're looking really focused in on two segments and you say, okay, I've got a horizontal curve, it's curving in plan. That means my segments are going to be a little bit wedge shaped. What does that mean in the local sense for these two segments? What is the relative degree of wedge shape that I need for those two segments to get it to match up and follow the curve when I erect them out in space. So you are zooming in on two pieces, looking at the relative relationship between two pieces, adjusting that as you cast it, and then when you take it out in the field, they fit together the right way. So let's see here. This is another little video. It's kind of hard to imagine. So over on the left is the span that you want to cast. So that's what you hope to achieve. You can see it's at a really strong horizontal curve. So we're just going to look at the plan view for the moment to simplify a little bit. But you take that span, you divide it up. So this is chopping it up into your segments. This is what you're going to cast. And you want to cast this red one here. And you've already cast the blue one here. So the blue one you adjust back and forth until its shape relative to the form matches what you want in the field. That was what that green light was supposed to indicate. Once you do, you cast it, you move that segment out, and you repeat the process, maintaining the relationship between those two segments. The exact same logic that you saw there in plan view, sort of adjusting the match cast segment back and forth so that you have the right wedge shape. That's exactly what you do for a vertical curve. That's what you do for a twist if you have a change in crossfall from one segment to the next. So one of the tougher concepts to get through, but absolutely key to being able to cast things off site and bring them to the site and assemble them and have them follow the geometry. A little bit of terminology when it comes to that. Now I want to say this is a bit of an old school picture. This is the way it's done for decades. You see some newer methodologies, but the idea is the same. So over here in red, you've got the match cast segment. So that was cast with a number of geometry control hardware embedded in it. You have hairpins. Those are those little things, and those are typically used to survey in the plan geometry. If you're curving, how much should these hairpins be offset from a straight line from the segment that you're about to cast? That's what this little distance here is. You also have elevation bolts, so that controls the vertical geometry. How much higher should this face be than that face if you're going in a vertical curve? How much difference should there be between the two sides if you're going through a crossfall relative to each other? And again, it's all a relative measurement. How much higher is this side, adjust it, and that creates the geometry. So like I said, there are other ways to do this. You see different arrangements, but the idea is the same, is how much do I adjust my match cast segment to recreate that relationship between those two segments in the field. A related but different topic is camber. So camber and geometry control are a bit different. Camber means that you are casting at a different place than the alignment. You may have an alignment curve that is flat, but because you know there are going to be displacements between the time you build the bridge and the time you're done, that can be superimposed dead loads, paving, it can be creep and shrinkage, it can be the effects of post-tensioning. You compensate for those with a camber curve. So that's kind of in addition to the alignment they're trying to cast. So, and this is a real good illustration of that. So you've got this beautiful curve that you want to grab, that's your final profile. You know, maybe you have long-term losses from creep, it'll creep down. The camber is just the opposite of those long-term displacements, right? So this is down 6 inches, this is up 6 inches. And then your casting curve, what you actually cast in the casting yard, is a combination of those two things. So that's what you see here in the bottom two. The blue is the alignment that you want. The green is the offset from that alignment to account for your long-term or your movements during construction. All right, 2 topics to go here. So post-tensioning. Post-tensioning and segmental are really hand in hand. You can't have segmental without post-tensioning. So it's important to understand how it works and what the parts and pieces are. Now, since this is 101, you hear words pre-stressed and post-tensioned. If you're not used to it, you may say, what's the difference? Who cares? Why does that old engineer keep correcting me when I use the wrong one? Pre and post of what? Well, pre and post of concrete hardening. Pre-stressed means you stress the tendon before the concrete is hardened, usually in an empty form, something like that. And then it is released onto the concrete, but the stressing comes before you have concrete. Post-tensioned is on hardened concrete. So you cast it, let it harden, and then you install and stress the tendons. And that means that you have to have special embedded hardware to put the tendons in and to stress it and to transfer that force into the concrete. So a quick rundown on what some of those parts and pieces are. You have strands. So you have individual strands of tendons. Each strand is usually composed of 7 wires, and one strand is, ballpark the diameter of your finger, maybe your thumb. Multiple strands create a tendon. You have them anywhere from 4 strands up to 30-ish. Those are the force from those strands is transferred to the concrete through the anchorage. That's this metal piece here. For segmental, you see a lot of these multi-plate anchorages. That means you have multiple fins through the anchorage hardware. Each individual strand goes into a wedge plate. That's that darker piece here, where it's anchored with a wedge. These wedges are usually 3-part wedges with teeth on them. That's what grabs into each individual strand and holds it fast into this wedge plate that bears against the anchor plate. You also have a spiral or some kind of confinement reinforcement, and that helps the concrete be able to handle that big compression load that the anchor is transmitting to it locally. And then you have the ducts sort of along the length. Oh, I forgot the cap, but we'll talk about the cap in a minute. So here's a nice review. This is all one project. This is sort of the life cycle of post-tensioning hardware as it gets built and installed in the field. This is a collection of those anchor plates. You can see the multi-plate anchorages just sitting there waiting to get assembled. This is after they've been assembled with the gathering collar and everything that comes in front of them, sort of to pinch the strands together, the rest of the hardware. Here they are tied into a very not congested pier segment. So you can see these are all the anchors there with some of the forming around them for the blockouts. This is what they look like after they get cast. This is just the back face of the anchorage itself. You don't have a wedge plate on yet. And then as it goes into the field, you can see the wedge plates have been installed. Some of them have the strands installed, and one of them is there being stressed. So that's kind of an overview of the life cycle of how those things come together. Now, there are 2 different types of post-tensioning, 2 different families, internal and external post-tensioning. So again, internal and external of what? The answer is the concrete section. An internal tendon is contained within the concrete cross-section. So that's when you see holes in the concrete cross-section like these. There's a duct running longitudinally from one side to the other. It's part of the concrete section. Here they are before they get cast. So with internal, these are some of the things that you normally associate with them. You have embedded anchors, of course. So this is like for a cantilever tendon where you would have access to the face to stress it as you're building. Internal tendons are where you tend to see blisters. Blisters usually house intermediate anchors. So after you have to give access to those tendons after the construction. And then you have internal deviations. So all the curves and all the twists and turns of these tendons are taking place inside the concrete. So that takes some careful detailing. You need to make sure that they don't pull out of the concrete, but they're properly reinforced inside the concrete. Most of the time with internal tendons, you see ducts that look like this. Kind of older times, and in some jurisdictions, California is one, you still see a lot of corrugated galvanized duct. Mostly that's falling to the wayside, and you're seeing a lot more plastic corrugated duct. Those are used with internal tendons. The caveat to that, and we'll see it in a second, is when you are injecting it with wax, the flexible fillers, those use smooth ducts for internal tendons. So as that catches on, you'll see a bit of a transition there. Another thing that you see with internal tendons sometimes are duct couplers. So, you want to keep the inside in and the outside out. Duct couplers are a good way of sealing segments at the joints. Water is a harder time getting in, and things like grout or flexible filler have a harder time getting out. So it's a seal, a 2-part thing that is cast into the segment. You can see half of it there. The orange half would have been embedded in the segment. That can be cast in. You don't always use these. This is really a case-by-case and spec-by-spec set of requirements. So again, read your specs carefully to make sure you know what's required for your project. External tendons. So external is external to the concrete cross-section, but not external to the world necessarily. They're usually inside the void inside a trapezoidal box girder. So they're protected from the elements. It's not going to snow on them. The sun's not going to shine on them, but they are not part of the concrete cross-section. They're sort of inside the chamber there, like you see on the right. With those, you have to have some way to deviate them. So you've got these tendons that are inside this chamber, and you want a draped profile, so you need some way for them to change the direction to follow that draped tendon profile that we talked about. And those are usually accomplished with some sort of special deviator segment. So it's a big force when these things change direction. You know, they want to straighten out. So you need something to transfer that force, and you can see that's what's happening here with these deviator segments that takes that deviation force and distributes it to the webs. A couple of different ways to achieve that deviation, looking at how you can do that. And sorry, it's the best picture I could find, but the bottom left is steel pipes. So the tendon would clamp onto a steel pipe. The steel pipe would have a curved radius, you know, and the tendon would run inside that pipe, and that would be cast in and embedded into this deviator segment that you see here. Another way is diabolo. You may have come across that word. Diabolo is basically a formed bell shape that follows a curve. So this is a diabolo. This is basically just forming it. When you pull it out, you just have a bell-shaped void. And in that case, the tendon and the duct is just continuous through this voided opening. Why would you want one over the other? It's a question of accuracy versus space. You can see right off the gate the diabolos are bigger. So if you have heavy reinforcement, you know, you have more to try to work around when it comes to diabolos. The upside is they're very tolerant for geometry, right? These, you know, they have to follow the tendon path easy enough when it's straight, but when you have curved sections, when you have vertical profiles and a lot going on in geometry, it's harder to make sure that they line up so that they are in exactly the right place. So it's a question of tolerance on rebar versus tolerance on tendon installation. And then external tendons usually use smooth HDPE ducts, the black ones like you see here. Transverse PTs, the last part I think I'll talk about here on post-tensioning. So transverse post-tensioning, these are usually in the deck. They're usually very small tendons. They're the white ones that you see here running transverse to the main longitudinal ducts. They compress the deck. They're great for durability. They do need to fit in a small space, so usually use the oval ducts to fit them in to sort of shoot the gap there on the very thin top flange. Oh, not at all the last topic, is it? So post-tensioning and protection. Used grout. Grout is a kind of catch-all. Historically, grout has been used to fill the void inside the tendons and to give the tendon the protection against corrosion. So this is sort of a sawed-off cross-section here. You can see the gray grout. You know, this is a good job on the grouting. You can see it surrounding all of the different strands and providing the protection. No voids, everything looked great. Been an evolution over the years from sort of quick and dirty cement grouts to prepackaged grouts, and even an evolution in some places, again, Florida leading the way of using wax and grease. You know, the idea being that the protection of these tendons is really quite critical to the longevity and the serviceability of these bridges. So it is very important to do a good job. It's important to pay attention to what you're doing and make sure that you do a good job. Last thing about grout, they're part of the anchorage protection too. That's certainly a place that needs corrosion protection. This is, since I stole it off the internet, might as well give them the plug, a picture from a VSL anchorage. It's a cutaway view showing the inside. It doesn't actually have this hole here, but you can see this is the wedge plate here. You can see a little bit of the strands poking out of their wedges right there. This is part of the grouting system. It would get filled with the flexible filler or the grout, whatever it is that you're using to protect that anchorage and the strands. Depending on the jurisdiction and sort of the corrosion environment, you may also be required to cover this in an epoxy or a mastic. You may be required to put a secondary concrete cap over it for protection. Again, read your specs carefully on those. And shameless plug, I know Greg mentioned it earlier, but the best place to learn about that stuff, and it is very important, is in one of the ASBI grout certification trainings. I've done it myself. We send our engineers every once in a while to make sure we're up to date. It's a great experience, so it is important, so it's worth sending somebody or going yourself. Last big topic, looking at some of the equipment. I mentioned specialized equipment a few times, and here we're really going to take a look at what that is. So starting with cast in place, again going through, and the big thing on cast in place is the form traveler. So again, the name says it all. We're not a very creative industry. It's a form. It's what you use to form each segment as you're building your way out, in this case in a cantilever. And the traveler, it needs to be able to move, right? It's every time you cast a segment and it hardens, you want to be able to push it out so that you can cast the next piece. So right there in the name, a lot of time you hear the term horses associated with form travelers. So I guess this look a bit like a horse head. and you usually have 1 horse per web. So this is really the structural member that takes the weight of all this wet concrete that's going to be here in the form and ties it into the existing concrete structure. So the strongest, stiffest place to do that is at the web. So you can tell this is a 3-web box girder because there are 3 horses. So it needs to be able to support the weight. It's a big structural member. It needs to be able to move, and it needs to be able to adjust so that you can match your geometry, right? This, where do I sit my forms to get my shape? They do get a little more complicated as you start looking at other types of construction. So when you have things like stays to worry about and kind of funny shapes to avoid, you need a lot of raising and lowering to advance them. So they can get to be very complex. They can get to be very heavy, and it can be a pretty important part of the design, right? It's on the order of 50 to 60% of the weight of a segment. So it is significant when you're looking at the construction engineering. Now for precast, one of the biggest tools that we use is gantry. So this is basically a piece of equipment that assembles the segments into their final position. It's how you support all of these things temporarily as you are doing that epoxy and you're installing the post-tensioning tendons to hold them together. So ideally it is both strong and able to move. So you want to be able to build a span and then launch forward to the next span, and again, adjust for geometry. You can use gantries for both simple spans and balanced cantilever, and you see a couple of pictures of each. Over on the right, you can see kind of what the job is for a simple span, right? You need to be able to support the entire weight of the span between the two piers with the gantry. So you're carrying a pretty big load. The spans are generally not as long. A balanced cantilever on the other side, you see over on the left, because the spans are generally longer, you need a longer gantry, but it's really only carrying and assembling one segment at a time as you're working your way out and cantilever. So 2 different jobs for the 2 different pieces of equipment. These are also very, very significant. I mean, just pull a number, they're going to be at least 200, 300, 400 tons, sort of depending on the span length that you're trying to work with and the size of your segments. They're very significant. And take a second to sort of get the nuance of what the picture is you're looking here. So you've got a simple span that's built, it's bearing on its bearing over here. This gantry that weighs hundreds of tons is sitting on top of it. It's supporting the weight of the next span. All of this is hanging off the gantry, which means it's going through these legs, which means it's going through this bearing. So a lot of weight and a lot of thought and engineering needs to go into these temporary steps and making sure that the bridge can carry them when it's built. So going to march through the different types of gantry, sort of from simplest to most complex. There are 3 of them, starting with an underslung gantry. This has got a long history. It's a very simple way of doing things. You can see the underslung gantries are just beams or trusses supported on the columns. So you have brackets on the columns. The segments right on top sort of sit in the armpit there between the top flange and the web. And they're supported, all of them are supported by this truss. These can be fairly low cost. You can really make them low tech if you want. There's some cases where they're even advanced with cranes, so they don't have a lot of moving parts. The next step up is a more self-contained, sort of all-in-one solution with an overhead gantry. You might expect this goes over the segments instead of under, and tends to be have a lot more bells and whistles when it comes to the self-launching and the geometric capabilities. So this is an example of an overhead gantry. You can use them to deliver segments from behind, so you can deliver them to the tail and then bring them forward. Or if you have access right below, you can pick them straight up from below. And then the third one, which is the more complicated type, is called an articulated gantry. So the articulation is really to get around tight curves. So what you're looking at in this picture here, if you look at this blue joint, that is a joint that allows this lower part to swing and plan relative to the upper part. So it's a good help when you need to navigate tight corners, when you're working in really congested urban areas with tight curves. That's when you would start looking at the investment and the fancier type of erection gantries. Do have one more video here, so taking a look at how this works in practice. Now there are lots of different ways to do this. This is just one of them, but how do you put these segments together? How do you stress them together, get the PT in? So this is showing a little bit of the sequence. This is a simple span being erected. You can see the gantry is going to hang all of the different segments for that span. And you can see it needs a little bit of room because these segments need to be put together one by one or pair by pair with the epoxy and the post-tensioning bars. So you want to get all of the segments hung, staggering them to create a little bit of space, and then start at one end with the pier segment and start attaching the segments one by one. So epoxy and PT together, epoxy and PT together, and then the last segment needs a little bit of room between where you're going to set it down and that front leg, and then the segment gets set down, tendons are stressed, and the gantry can advance forward to the next span. So that is a visualization of one way of that coming together. There are variations, but it's all sort of the same theme. A couple more pieces of equipment, lifters, beam and winches. These are quick, simple, easy, a lot like a form traveler in the way that they're designed. You're just using them to pick from the tip of a cantilever usually. You know, simple and cheap, but you do need access right below them to be able to deliver the segments right under the lifter. And don't forget that you're going to need to move these segments around quite a bit. So you need equipment to move and transport the segments in the casting yard, on the site, sometimes on top of the deck. So you need to make sure that your equipment that you have to move things around is integrated with how you're going to use it. If a flatbed truck works, great, you can do that. Cranes are great if you have the space. Sometimes when you're moving things on the as-built structure, you want something a little more customized like what you see here. And really the last thought to leave you with is that it needs to be integrated. These are 3 pictures from the same project. On the left, you have the casting yard, the segments being moved. In the middle, you have the transporter that was used on site. And then on the right, you have the erection gantry, which is also picking them up with a winch and taking them to the tip of the cantilever. So 3 different picks. You want to use all the same equipment. You want to make sure things are integrated and sort of interoperable with the ways that you're going to pick up and handle and transport things. Something worth thinking through. So that is it. I will stop my monologue here and turn it over to Tim.
Hey,
I took up pretty much the entire time, but I'm happy to stay on for a bit and answer some questions.
Great, Ben. Fantastic presentation. And again, yeah, we are running just a little bit long, but that's fine. If folks need to log out here, you know, now that we're a little bit past the top of the hour, that's fine. You can log out. We are going to make a PDF of the slides available, and then a link to the recording will also be available. So if you can't stay for the Q&A, you could certainly catch a lot of it then on the video, the recording. We'll try to get through maybe in a few minutes here some quick Q&A. Tim Berry is going to join us to lead as a moderator for our Q&A. Tim's a vice president and area manager for RS&H in the construction management practice. He has over 20 years of experience, including construction of 5 segmental bridges in Florida and Virginia. He's now working on a repair project up in Seattle. He's been involved with ASBI for a really long time and is currently the chair of our ASBI grouting committee and the past chair of our construction practices committee. So with that, I'm going to turn it over to Tim and Ben to kind of go through some of the questions that have been asked so far.
Thank you, Greg, and thank you, Ben. Also, that was really good presentation. A lot of good questions here, so we'll try to start running through these, Ben. So let me start right off the top. Question about the diaphragms. The question is: are the diaphragms typically installed with the precast piece prior to erection? So I assume this is referring to essentially the pier segment.
Yeah, that's right. It's all one monolithic pour, typically 90% of the time. Occasionally, you'll find ones that are just too heavy. This is usually really deep things. You see this unbalanced cantilevers where you may have some cast in place components of it. You know, off the cuff advice is to steer clear of that if you can. It does add a lot of complexity. So the basic assumption is that they are part of the precast segment, and usually the heaviest segment, as you might imagine. Because of that, they tend to be shorter for that reason.
Yeah, and I'll just add to that. Sometimes on projects, because of the weight, they will be actually split in halves, and so they're, you know, for either transport or for just handling equipment, that they'll split it and then epoxy it together and post tension together like you would any other pair of the segment. So yeah, because that is definitely a problem when they get too big. It tends to control what size equipment you need on site. So next question involved cable stay. There's a question is, obviously you talked about the cable stays and how their involvement is there still post-tensioning involved with a cable stay segment?
Yes, there absolutely is. It's very much a case-by-case sort of, most cable stays are pretty unique, but the cables don't do it all. You definitely need some continuity. You still have things like epoxy if you're doing a precast that you need to put together with PT bars. And a lot of times you'll see a lot of cantilever tendons sort of close to the pier to try to save one stay's worth of spacing and build it as a balanced cantilever. So absolutely there is. Stays don't do it all. The volume and the ratios are a lot lower, as you might imagine. The stays are certainly there for a reason, but you have some.
Okay, this next one you could answer for probably about the next hour, but I think it's a really good question. Is what kind of quality control measures in the field are used for both precast and cast in place, particularly as it relates to tendon profiles?
Oh yeah, boy. You could write 100 pages of specs on that question. But yeah, it is a good question, and it is, I think it touches on the heart of something that is very important for all of this, is that you are building a lot of things that you're not going to test out until later when you actually assemble them. And tendons are a good example, right? You want your tendons to be well aligned because, if you have things like mismatches and kinks across the tendon joints, you can have wire breaks and things like that when you come to stress them, or in an absolute worst case, you can have a concrete pop out. So it is something that you want to pay very close attention to, and to answer the question about the QA, there's no substitute for a well-educated person paying close attention. You can write all the specs you want, but you want your inspectors in the field to understand the goals, to have nice, smooth transitions, to have a lot of familiarity with the shop drawings of what it should look like and sort of what's important and why, and then paying attention day after day as you see them coming through the form.
Okay, I think you hit the nail on the head. Yeah, in precast in particular, you're laying out these tendon profiles of your casting that aren't going to be. You're not going to know if it's right months, sometimes years later. So you got to get it right the first time. There's no second chance at those. But yeah, the inspection in the field, and especially in a casting area, is crucial to have good people doing that inspection. Next question we had is it's again another complicated one. I'm going to kind of change it a little bit. It talks about how the different types of segmentals rate in terms of cost and time, and there's no real answer to that. So I guess what I'm going to ask is, what are the driving factors of how you choose either precast or cast in place, or even balanced cantilever, or a span by span? What are the factors that go into making that?
Yeah, sure. So not the kind of person that likes to throw out dollar values, because it is hard to get a handle on. Varies a lot by location, by country, by type, by circumstances. But as a broad rule, shorter is cheaper, right? Down to a point. So simple spans, things that are in the 120 to 150 foot range, those are going to be cheaper structures to build than a 300 foot, 400 foot balanced cantilever. So, you do the hard things, you do the expensive things because you have to. You have clearance envelopes, you have something that you've got to get across. And then, so that's, if you're sitting at a total greenfield, you'd start as cheap as you can in short spans and very simple repetitive things, and then move your way up through the more complex types, through balanced cantilever, through cast in place balanced cantilever with long spans, into cable stays and that kind of thing, as you need. Now, making decisions between cast in place and precast, a lot of that really comes down to volume most of the time. So cast in place, tends to be a little bit slower in the field, at least in terms of the amount of time that you spend, but the investment is low. The form travelers are relatively cheap compared to a casting yard and any kind of erection gantry. So if you're doing a 3-span unit, or you have a project with 2 or 3 of them along the length, cast in place makes a lot of sense. It keeps the investment down. If you've got, dozens of them back to back, then you start looking at, well, is it worth the investment for me? You go through and look, how many forms do I need? Where do I have a casting yard? What is my gantry going to cost? And seeing if that starts to make sense. And the schedule saving and the efficiency that you get out of the precasting operations.
Okay, yeah, thank you. That's certainly an abbreviated answer, because that's another one that could go on for
Yeah.
weeks. And whoever asked that question, the reason I did change it is because it's never that simple to just always say, well, this one's always going to be cheaper. It so much depends on site conditions, different other factors. So it's more of a matter of fitting whichever one best fits your project. And sometimes what you think might be more expensive actually is cheaper. So it's never going to be as simple as, well, this one's always the cheapest, this one's always the best, this one's always the best. It's much too determined on what the actual specifics are of that project.
Yeah, absolutely. And you never know. You can have a contractor that owns a bunch of form travelers, and so they're going to be inclined to do that. So you just never know. It is very situational.
Similar question, you talked briefly about long line casting versus short line. Again, what drives that decision? And you said long line is not very common. What would be a consideration for a contractor using either of those?
I'll be honest with you, I don't know. I've never done it myself, and there are only a handful of projects that I've seen in the past that have done it. It tends to be more of a legacy method, and the only times I've seen it have been really, really big segments. So I'm guessing that it is, you don't want the headache of moving them around quite as much, and or if you have real concerns about the geometry and you really want to, when you're doing short line casting, boy, if you get the sign convention going the wrong way, you've got a big problem. When you're doing long line, it's a lot easier to visualize what you're doing. It's all laid out there in front of you, and it's easy to map it onto the alignment. But I have to admit, it's a little bit of a hole in my education, never having done one before.
Same with me. I've never actually seen the long line, but the person who asked the question, I think he's probably got a valid point too. Probably a lot of it has to do with space in the yard, because with long line you have to have room to be able to lay it out, and sometimes you just don't have that kind of casting. So that's
true too. Yep.
Is there a typical or a routine design check that needs to be done for the transportation or the handling of segments?
Yes, there absolutely is, and glad you brought that up. So, when you lift any of these, you've got some kind of lifting device. If you think about looking at those pictures of the different gantries, the overhead ones usually have rods. You can see it on the screen right now. Those go into a hole in the top flange, and there's a plate on the backside that holds it up. When you look at those underslung gantries, they're sort of, the flange is resting on the gantry. And the main thing that you have to worry about is the top flange. So all of these are putting some kind of demand on the top flange and sort of bending that slab. So you're looking at, local punching shear, you're looking at bearing stresses, you're looking at bending in the top flange. Not the hardest engineering calcs in the world to do, but definitely a step that needs to be taken.
Okay, we're kind of run through about three more here. There's three more that are actually, I think, pretty important. One, and I think you're going to twist the answer a little bit, but the question is actually, what are the tolerances for fit up between precast segments? So I answer that how you want, Ben, but I think it's important to probably maybe explain how that fit up occurs and the importance of match cast.
Yeah, and don't want to run afoul of somebody's specs if you're, giving an answer that's different than your project spec there in front of you. But when you talk about fit up, so you cast the segments, you do the match casting, you take them apart, sit out in the yard for a month to a year, and bring them onto the site and put them together, and there will be slight misalignments. You will see lips in the ways that the segments match up. It's imperfect, and usually those are quite small. Most of projects you will see a table sort of listed as the various tolerances for fit up, things like that, and they're small numbers, 1/16 of an inch, 1/8 of an inch, things like that. But they can happen, and those tolerances are written sort of case by case in terms of what you need. So what do I mean by that? Like you might have a tighter tolerance if you have an as-cast writing surface than if you are planning an overlay. You know, if you're in somewhere that is very visible and you're really shooting for an aesthetic statement as opposed to, you know, a more industrial working class type bridge. So read your specs, but those are usually tabulated for the different faces and the different locations of what's allowed for a fit up. It's not zero. It's not very big either.
Yeah, and it's important in a quality control is that the face of the segment, you know, generally isn't touched. You can't have anything, you know, impeding, because fit up and tolerance is important because you want to have a watertight seal. That's really the main purpose of the epoxy. So if you don't fit up well and you have a gap there, you're going to have water leaking in. That's a really bad thing. So that's why fit up and that tolerance is actually really important. One last one here, and this is a good one also. What happens when you, at your mid-span closure joint, when the two cantilever tips do not meet or are not at the same level? Basically, what is done to overcome that?
Yeah. Again, great question.
It happens, by the way. It's a good question.
It absolutely does happen. So a combination of different things. And I'm glad it got brought up. But the short answer is you push them together. You know, really, what choice do you have, right? You have two tips. You need to have a completed bridge. You know, and assuming that they're within reason, you push them together. Now, every project should have some sort of alignment system for them, some sort of strong back beams that bridge that gap. Even if your alignment is absolutely perfect, you need to hold them steady while that closure pore is curing and you're stressing the tendons. So you're going to have that out there, and you know, you should plan ahead. And that starts with the engineer. It starts with reading the requirements of AASHTO, which do have some requirements for being able to adjust the tips for geometry. That should sort of be built into the design. The contractor and construction engineer should also be aware that that is a thing that is likely to happen. So when they go to design those strong backs, you know, it should be for some force. And you should have a construction engineer sort of running numbers and saying, okay, if I need to align them an inch vertically, what does that take? So it should be an engineered solution, starting with the design and some communication of what's built in, and then flowing all the way through in the construction engineer and the equipment design.
My cop-out answer to that question is always don't let it happen. So that's why geometry control is incredibly important. But I understand that that's not a simple answer. But yeah, your life becomes much easier if you have good geometry control and you minimize that from ever occurring. Well, unfortunately, we're out of time. There's a ton of good questions. We really appreciate the feedback. But we could go probably for another hour, but we don't want to do that. So, Greg, I'm going to turn it back over to you. Thank you again, Ben. This was really good. Ton of information.
All right. Well, thank you guys for the Q&A, and we'll try to post up some of the answers to the questions we didn't get to on our website. I will mention, I'm going to put it up in the chat. Some of the questions that have been asked, there's more information in our construction practices handbook, and it's available as a free download from the ASBI website. I put a link in the chat that's a direct link. Just it requests a little bit of contact information so we can get in touch with you when a new version comes out. If you're watching this video, you won't have access to the chat. So what you can do is go to the ASBI website and go to the publications tab, and you'll be able to find the construction practices handbook. And as a final reminder, PDH certificates, we'll send those via email in about a week. Go ahead and register for the March and April webinars. This is a good intro to some of the information you're going to see in our other webinars in March and April. The registration is open on our website already. A recording of today's session will be available as well. So if you have colleagues that weren't able to attend today and you'd like for them to see this content here later today, probably by tomorrow, we should have then the link up to the recording of today's session. And then again, we'll also put up the PDF of the slides. So again, Ben, can't thank you enough. Every time you speak, I learn more, and this was real educational for me, particularly the in-depth information on geometry control. was really useful, at least for me personally. So thank you, Ben.
Yeah,
And
my
thank
pleasure.
you. Yes. And thank you to everybody for attending today. And with that, we will be signing off. So everybody have a good rest of your week.